So we want to see what relationship is there between ionic product, solubility product, and precipitation. Which relationship is there between ionic product, KSP, and precipitation? This is what I have for you under this. You are aware that for any sparingly soluble electrolyte, KSP is always equal to the ions, concentrations of the ions, power their stoichiometric coefficients in the solubility equation. I think when I write this, you understand what I mean. That is KSP. At the same time, what we call ionic product is the same expression, surprisingly. So both solubility product and ionic product have the same expressions. Where is the difference? That should be the question lingering in your mind now. The two have the same expressions. They are not different. The only difference is that ionic product is applicable to all types of solutions at any concentrations. Applicable to all types of solutions. At any concentration. So there we don't limit the concentration. It can be applicable to solutions of soluble compounds, solutions of sparingly soluble compounds, to any solution. Actually, there you just multiply the product of the concentrations of the ions in the solutions. That's what you do. You just multiply the product of the concentrations of the ions in those solutions, and you power them with their stoichiometric coefficients in the equation. And it increases with the increase in the concentration of the ions. However, solubility product is only applicable to saturated solutions. That's the difference. We only apply solubility product to saturated solutions. Once a solution is not saturated, then we cannot think of solubility product. I think you know what I mean by saturated solution.
Yes, teacher.
Now, how do we relate solubility product, ionic product, and precipitation? I'll put that in a very small table here. I'm going to consider a smaller table here. When I have KSP greater than ionic product, when I have KSP greater than ionic product, I think I should write this very well. This is power X, concentration of B, X minus power Y. That is one condition. Can have KSP equal to A Y plus X. This is B X minus Y. I can have KSP less than A, concentration of A power x, concentration of B power y. This is what I call, in both the three cases, this is what I call the ionic product. If you have a solution where KSP is greater than ionic product, you calculate and you see that KSP is greater than ionic product, then that solution is not saturated. Solution is not yet saturated. More of the electrolyte can dissolve. In other words, when sorbate product is greater than ionic product, more of the electrolyte can dissolve, since the solution is not saturated. Okay? When ionic product is less than, in this case, when ionic product is less than sorbate product, more of the sparingly soluble salt dissolves and the solution is not saturated. When KSP is equal to the ionic product, the solution is saturated. When the two are equal, the solution, that's what we call, that's when we say the solution is saturated, is an equilibrium. There is a dynamic equilibrium, which we explained previously. So the solution is saturated and cannot dissolve any more electrolyte. Cannot dissolve any more electrolyte. When KSP is less than solubility product, when KSP is less than solubility product, or no, sorry, when KSP is less than ionic product, or when ionic product is greater than KSP, that is the condition where precipitation occurs. Precipitation of sparingly soluble compound occurs. And this is the main important concept I want us to understand. Whenever you see precipitation occurring, that implies that the solubility product is less than the ionic product. In other words, the ionic product exceeds KSP. It exceeds the solubility product. Have you got the three conditions?
Yes, teacher.
So if you've got the three conditions, those are conditions we are going to use to explain precipitation. And you can be given a question, as we shall see later in our calculations, where you have to apply that. Let me see the most common question here. This question says, when ammonia solution is added to magnesium chloride solution, a white precipitate insoluble in excess is formed. But when the same solution is added to calcium chloride, no observable change occurs. Explain. I hope you will not write as me. My handwriting is not so good. When you add ammonia solution to magnesium chloride solution, white precipitate insoluble in excess is formed. You see these observations in practicals. We are now explaining them theoretically. When the same solution is added to calcium chloride, no observable change occurs. What causes this? This is still a two-divided question. Attack the first side. Explain why when I add ammonia solution to magnesium chloride, there is a formation of a white precipitate insoluble in excess. Let's first attack that side. So what causes that? It's because of precipitation of magnesium hydroxide, right? Magnesium ions react with hydroxide ions, form insoluble magnesium hydroxide. Why is that reaction able to occur? It is because the ionic product of magnesium hydroxide in that case exceeds its solubility product. Hence, precipitation can occur. So what will you have to say? You have to say that magnesium ions I said I'm using a formulae here due to the space I have, but in exams you use the words. Magnesium ions react with hydroxide ions. These hydroxide ions come from ammonia solution. You are aware from ionic equilibria that ammonia solution ionizes to form ammonium ions and hydroxide ions. So the magnesium ions react with the hydroxide ions to form insoluble or sparingly soluble magnesium hydroxide. Because why is that able to happen? Because the ionic product of magnesium hydroxide exceeds its solubility product. So that's where the idea now comes in. If precipitation occurs, it's because the ionic product has exceeded the solubility product. It's greater than the solubility product. At a point where the two are equal, the solution is not saturated. I mean, the solution is saturated and cannot dissolve any more electrolyte. At a point where the ionic product is less than the solubility product, solution is not saturated, more electrolyte can dissolve. At that point, no precipitation can occur. So that's the concept I'm trying to bring in here. Because the ionic product of magnesium hydroxide exceeds its solubility product. So that's the white precipitate that is formed, insoluble magnesium hydroxide. Why is it insoluble in excess ammonia? We may not go into that detail. If it was sodium hydroxide, we would say it's because it is basic. But with ammonia being a stronger base, solubility in excess would be due to complex ion formation. So here we shall not go into those details. So write equation. Write equation to show that reaction. So that is plus 2 hydroxide ions to give us magnesium hydroxide, the white precipitate. Now attack the second part of the question. When the same solution is added to calcium chloride, no observable change occurs. That's where you bring in the concept of ammonia being a weak base. It cannot give us enough hydroxide ion concentration for the ionic product of magnesium hydroxide, calcium hydroxide in that case, to exceed its solubility product. So what do you say? You say ammonia is a weak base, comma, partially ionizing to form very few hydroxide ions. So you have ammonia, water, very weak base, partial ionizing to form ammonium ions and hydroxide ions. So after writing that, you say, this is the gist of the answer. The concentration of hydroxide ions formed by the weak ammonia base is very low for the ionic product of calcium hydroxide to exceed its solubility product. Therefore, no precipitation occurs. Are we together?
Yes, teacher.
Very good. If we are together,